a bachelor from Drexel University and his PhD from the University of Massachusetts Arbor. He held a postdoctoral fellowship at the Department of Terrestrial Magnetism of the Carnegie Institution of Washington, and a second postdoc at NRL before joining the NRL scientific staff. In January, Dr. Lockman transitioned to emeritus status, so he can concentrate on research full-time. In 1993, he became Green Bank Site Director, a position he held for 6 years before returning to the resident scientific staff in Green Bank. He has served on numerous advisory panels for the NSF and NASA, and in 2007 was elected to a 3-year term on the board of directors of the American Astronomical Society. Dr. Lockman's research interests include the structure of and evolution of the Milky Way and the structure of the interstellar medium. He's currently doing studies of gas flows into and out of the galaxies using the Green Bank telescope and other instruments to make extremely sensitive measurements of neutral hydrogen beyond the disk of the Milky Way. He recently discovered that there is a cloud of gas falling into the Milky Way that contains enough gas to make more than 1 million new stars like our sun. He's also involved in collaborations with scientists using the Planck satellite to study interstellar dust and the cosmic infrared background. He has published numerous articles in professional journals and edited several books, including Gaseous Halos of Galaxies and But It Was Fun. And another one, But It Was Fun. The first 40 years of radio astronomy at Green Bank. In 2013, he was elected as a fellow of the American Association for the Advancement of Science in recognition of his significant studies of neutral hydrogen in our galaxy, and for his service to U.S. radio astronomy. So, ladies and gentlemen, let me introduce, it's my pleasure to introduce you, Dr. Jay Lockman.
Thanks very much. As I'm sorry to have had to miss most of the entire conference, because looking over the program, it was really full of delightful things, but I just returned late last night from a 10-day vacation. And if you can imagine my state of mind, if you can put yourself back to your first morning after a vacation, and looking over the program, I realized that there were talks on most of the things that I might talk about from a scientific or technical nature as would apply to you all. So I'm going to start off in the grand tradition by showing you some vacation slides. We have a couple of the lights out here to show this up a little better. Yeah, for fluorescence go down, just you can bring up the incandescents. Here's where I spent the bulk of my time. Does anyone recognize this?
It looks like an upstate New York mill town.
Very good, very good. It's a Western Massachusetts mill town, and this was Sprague Electric.
Oh, okay.
Don't be vague. Ask for Sprague. I'm sure your devices have many. This is an old mill that started off, I think, as a textile mill before the Civil War on the Hoosick River in North Adams, Massachusetts. And I'll show you, it's delightful structures, amazing old buildings. Here's a courtyard, and they have these, that's a passageway up on top, and another courtyard showing this amazing structure. Well, after Sprague went out of business, it was taken over and turned into the Massachusetts Museum of Contemporary Art. And this is not modern art, this is contemporary art. They boast that they really don't have much of a permanent collection. Everything you see is brand new. And so, as you can imagine, it's pretty wild. Here shows some of the things over the years in there, various exhibits of various kinds. I really recommend it most highly. It's a wonderful thing. And this, I shot from below in one of the courtyards. This is a room that is about this wide and maybe 2 times longer, in which the artist has assembled light bulbs that is the mean color of light in the local universe. This kind of beige light. And so, in fact, there are these astronomical connections here in the midst of the modern art. But I didn't go just for the art, because every year around this time, they have a contemporary music festival, which brings contemporary music to contemporary art. And it is a magical, absolutely magical combination. And the one in the upper right shows a performance in that same room with all the lights. Bang on a Can is a collective out of Brooklyn that encourages contemporary music. This is their Loud Weekend. And last year, this is the photograph from last year, Yves Aglarian composed, and then they performed a piece for 24 double basses standing outside along that row of trees. And you just walked up and down while there was this amazing sound going on. A lot of digital work. Tristan Parrish is doing 1-bit music. And as I understand it, what he does is he generates tones, samples them at 1 bit, plays them back into a speaker. And in the case of this particular performance, was accompanied by a harpsichord, certainly one of the oldest of the working instruments. So it was a harpsichord and speakers playing 1-bit electronics. This is a sort of CD kind of thing you can buy of his music. It's generated on the spot, sampled, and then you plug your headphone in right here. So this was a really amazing combination of art and music and technology. And this shows this is their 25th year at the Museum of Contemporary Art. And this shows a poster that is at the back of one of the performance venues, showing some things about it. 24 acres, okay, 300,000 square feet of gallery space. At the top, you see the row of 27. That's 27 miles of HVAC system. I'm looking at this as a guy who once renovated a house, and I'm just thinking, what was the first thing that the engineer did when they realized they had this on their hands? They've got 1,938 solar panels in the upper right, all sorts of wonderful statistics about it. It's a marvelous place. But then what I noticed was something that the people working around the museum didn't notice and really had no explanation for. In the upper left of this figure, there's a UFO. I said, can you explain this? And they were very helpful, but I did not find anyone who could explain what that was doing. Which brings us back to Greenbank, of course. In Greenbank, as you all know, the site of Project Ozma, 1959, 1960, where Frank Drake, who was then just turned 30, did the first modern search for signals from extraterrestrial intelligence. Used what was then a state-of-the-art antenna and a state-of-the-art receiver for it. You know, in retrospect, and I sometimes give talks on SETI because it really is interesting to me. There's two ways to go about it. You could say, what would other civilizations be like? You know, where could life form? How could we make an informed search? But Frank just swung for the fences. He said, well, let's go and look, right? And looking with radio telescopes is cheap compared to almost any other aspect into the question of interstellar life. It was a very vibrant time here at Greenbank, it still is. But there was a scientist on staff a few years later, Sebastian von Horner, who was one of the wisest and most interesting men I've ever met, who got to thinking about music and interstellar space. And he says, a number of astronomers, scientists have tried to answer questions concerning life in space. Can we assume that life and intelligence have developed not only on Earth? Where could it be? How frequently, how far away, and where? But then the question that interested Sebastian was, at the bottom, what would we talk about? Well, we could talk about antennas, all right, if we're working with electronics, our receivers, in decreasing order, mathematics, physics, chemistry, biology, politics, religion. But where does music come in? How universal is it? How universal is our music? Would it be applicable? Would we be able to have musical exchanges with another civilization? And then follows about 15 pages of analysis of why we like music, the mathematical relationships with music, and so on. I keep forgetting that in 2010, Frank came back to Green Bank for the 50th anniversary of Project Ozma, and we repeated the experiment. And I say we because Karen O'Neill and I were his assistants at the controls of the Green Bank telescope. And we looked at the same stars, same frequency range, of course, about 1 million times more sensitive. A lot more RFI too, I'm sure you know. And the BBC sent a film crew there with a bucket of champagne. Of course, we didn't see anything, and I never could find out what happened to that champagne. But it's been a continual activity here at Green Bank, now privately funded through the Breakthrough Listen project, that's turning up lots of interesting things. Frank also convened in the Drake Lounge the first meeting to discuss the possibility of extraterrestrial intelligence. And that was in November 1961. There's a plaque I'm sure you've seen in the lounge with the so-called Drake equation. And the Drake equation was intended to be a program for this meeting, a way of organizing thinking about the possibilities, the quantities, the factors that go into determining if there's a communicating civilization somewhere that we could speak with. So it's a very funny equation looked at from a mathematical point of view. And I tend to think of it more like a recipe. The ingredients that you would need for a communicating civilization to talk to us. And first of all, the number of stars in the Milky Way, even back then, 1961, we had a pretty good idea of the number of stars in the Milky Way. And in fact, for many of the audiences that I speak to on this topic, I have to back up and say, hey, let me tell you what the Milky Way is, okay, all kinds of stars. But you can see right away that we've got a restriction going on here. It's assumed that any communicating civilization would be on a planet around a star. Now, there have been science fiction articles written about vast, diverse, diffuse intelligences in clouds and so on. It's hard to know what we would have to say to them. It's hard to know what they would have to say to us. So right away, Frank was restricting it down. You know, a star is a wonderful thing. It provides energy. If you got a planet, you have a place to dump the energy. And so you have an engine, right? One side's hot, the other side's cool. You can develop life. You can do all sorts of marvelous things. And so the question was, how many stars had planets? And at this time of this meeting, and for the next 30 years, the answer was they didn't know, because it was only around 1990, in the 1990s, that we discovered other planets around stars. Big question mark. And there were theories that said that stars during their formation and early evolution would sweep material pretty clear. But we now know that there are stars, that there are basically every planet, every star has planets. It really feels like a Monday morning, I'm sorry. Every star in the Milky Way certainly has planets. And let's see if this internet connection allows me to show this. This is something that NASA put together a few years ago, showing the known planets now. And this is, if it works, this is key to the discovery. Each year will start around 1991 and then go up in this case to 2022, when there were 5,000 planets known. But as each planet is discovered, there will be a tone which is proportional to the length of its years. Let's see if we work here. Oh, it's going to play from my laptop, so. One second, let me try something here. I don't know how to make this louder. Something I should have. There we go. There's the loud. There we go. All right, let's try again.
And online participants, are you seeing his video?
It was good at full screen.
Oh. There we go. Back to music, of course. date at the top. All right. A quick note before going on. It's superimposed, these planets are superimposed on a photograph of the Milky Way. And you can see the just band of dust and the flattened disk that is the Milky Way. And yet planets seem to be distributed almost uniformly around the sky. Why are we not seeing the Milky Way in the distribution of planets? And the answer is that all of these planets are close. We're embedded in it. We're not anywhere near sampling the variety of planets. As we get more and more and more, pretty soon we'll see more of them concentrated to the Milky Way where the stars are. But this just gives you a big, just good impression of how primitive our understanding is, that we don't even see out far enough to notice that we're in a disk of planets. Okay. No, thank you, we've done that. So I put checks on these items in Frank's equation where we have a pretty good idea, and question marks of various numbers where we know less and less. And as we go down the list, it gets less and less. Planets that could have life, not too hot or not too cold. Yes, we're getting a good census of planets now. And actually, technically, if you're interested, I'd be happy to discuss this more because it's marvelous the way these planets are detected. They are detected by the dimming of a star as the planet passes in front. And we're talking about a few hundred parts per million in many cases. You actually have to watch the star dim and then come back up again. And then repeat that a number of times to make sure you're seeing something that's truly a transiting event and not some funny fluctuation with the stars. The stars have a lot of noise. So right now, we're biased towards short period planets because we see those a number of times in any given year. And as time goes on, we'll get more and more of them. But the answer seems to be there's enough of them out there that seem like they're rocky with some water or ocean planets or whatever that could support life. Planets that develop life, well, we really don't know. Excuse me, we really don't know much about this at all. We know that life started on Earth about as soon as it could, about as soon as the Earth became hospitable without big rocks constantly falling on it. There's evidence for the simplest cells, bacteria. It took a long time after that for more complex life to develop. But it seems that given an energy source and given some time, and the other thing we know, of course, through radio astronomy, is that the galaxy is full of organic matter, full of organic molecules. I put much of this together last night. Some of these slides will be a surprise to me. Let's see what I did. Okay. Just let me just say, we now know that the dark clouds that are the sites of star and planet formation are teeming with complex organic molecules. And by organic, I mean based on the carbon bond. The carbon chemistry seems to be ubiquitous throughout the Milky Way and probably throughout the universe. Carbon really is special. And so if there is life elsewhere in the Milky Way, we are almost certainly related to it at the molecular level. Planets don't have to develop life from scratch. They can be seeded by complex organic molecules. So I think there's a good chance that given a quiet planet and a quiet star, you'll get life. And at that point, then planets that develop intelligent life. Well, now we're really way out in the wild blue yonder, but it seems to me intelligence is such a good thing for an organism to have that it will, I mean, look, it brought us here, right? On the top of the evolutionary heap. I think that the drive to evolve intelligence is pretty strong. So I have that down with a double question mark, but I think that if we get life and it's allowed to continue, then it'll eventually have intelligent life. Life with the ability to communicate with us. Again, now Frank's narrowing things down more and more and more. Super intelligent dolphins living on a water world will not be building antennas, will not have Society of Amateur Radio Astronomers meetings. And so we need something that's, and we really have no idea. We have only been in this stage for a bit over 100 years, the ability to communicate off planet, a little over 100 years. Which brings us to the last question, a lifetime of a communicating civilization. And I want to spend a little bit of time on this because this is, I mean, how long will we last as a communicating civilization? And the reason why I want to spend a little time is that this is the one term in all this over which you and I have some control. We have some control over the lifetime. And we can look at the kind of what you can call threats. I've broken it into 3 galactic threats, local threats, and internal threats to the lifetime of a communicating civilization. If a supernova went off nearby, that would be the end of us as a communicating civilization. And the supernova rate was much higher in the early life of the Milky Way than it is now. So that's what I mean by an external threat. You need the neighborhood to calm down enough to allow your intelligent life to evolve to the point, and we're almost at it. We're almost at the point where we could do some space engineering if we understood that a supernova was going to go off nearby. We could imagine building a shield and protecting ourselves from it. Say we're not there yet, but it's not out of the realm of our imagination if we decided we wanted to do this. So maybe a civilization has to get to that point where it can protect itself from, understand the threat and protect. This is not out of the question. Local threats. There are rocks that fall from the skies, right? This is the one that landed over Siberia 10 years ago or so. And had this is about the size of a school bus, I'm told, had to come in at a steep angle that could have killed 1 million people. Now, we know about this. And in fact, NASA, at the direction of Congress, has been directed to find and catalog all the things that could impact the Earth. You've heard of Apophis, this wonderful, it's not so wonderful, this big chunk of rock that's going to come by in, was it 2029? Yeah, 2029. It's going to come by below the communication satellites, below the geostationary belt. Will be visible by eye as it moves across the sky. I first heard about this at a conference, certainly 10 years ago, maybe longer than that, where they had just announced the discovery. And the scientists from NASA at that point said, there's a keyhole in space. And if Apophis passes through that in 2029, then it would return for impact in 2035. And they didn't know its orbit enough to know whether it was going to pass through that keyhole or not. Well, now we do, and it's not gonna. Okay, but it'll be quite a. But what this figure shows is the diameter in kilometers of these various rocks that are in the solar system, and impact interval, how long we can expect between impacts like that. And so you get things that are the diameter of many kilometers, you know, a few every million years. But the gap on the left is the gap between those that have been detected, the red line, and the assumed population. So that's where we need to fill in to measure the trajectory of these objects in there. But we're doing that now. And we've already proven that we can deflect asteroids or impacting objects. Doesn't take much energy. If you can just speed the thing up or slow it down by a few seconds, the Earth will have passed. And so we can do that now. And so we're beginning to, I think civilization gets hold of its local threats. Internal threats. And again, this is something we can do something about now. At that meeting in 1961, one of the participants was Phil Morrison, brilliant physicist, who also happened to be the guy who armed one of the nuclear bombs that was dropped on Japan. So he was very keenly aware of the threat to ourselves. And in fact, this is something that it's a puzzle to me. You know, we got where we were because of a kind of species-like aggression. But that's not a good quantity to have if you want to have a sustainable civilization. And somehow we have to turn this very admirable, aggressive quality that's built into all of us away from aggression and towards sustainability or growth, or something that gets us past the first few hundred years. Frank Drake himself thought that if we could detect another civilization, it would show that somebody somewhere got over their sustainability crisis. And that would mean we could do it. But we don't know right now. And so there's also the climate change problems. We've got to get that sort of sustainability. But that is something we can do something about. This is, you know. And let me just, well, there's another issue that I find really interesting. And there are historical precedents for this. In the Ming Dynasty around 1400, the emperor set out a fleet that may be unparalleled in human history to explore and discover. It was called the treasure fleet, and bring back tribute, bring back things. It started from northern China here and went all the way down around the Korean Peninsula, through this Borneo here, up through that way, up to around India, landing Strait of Hormuz, down the Horn of Africa. They brought back a giraffe for the emperor. It was just an amazing voyage. There were like 5 voyages of discovery and conquest and so on. And at that time, they had 3,500 vessels and 2,700 warships. Within 100 years, there was such a change in the attitude by the emperors of China that they ordered destruction of all ocean-going ships, and this entire civilization turned inward. This can happen. We can lose interest in exploring. We could lose interest in communication. And living here in Greenbank, so I've been here 30 years, 30 and a couple of years. And when we came here, mobile phones were something you'd only have if you were a surgeon and needed to be called to your operating theater. And we've stayed in the quiet zone. Okay? Our kids grew up here. They didn't have phones. None of their friends had phones, so it was okay. And I go out into the world periodically and I'm amazed by what I see. And it's sort of encapsulated in this cartoon. You've heard of the Fermi paradox. So let me just, Enrico Fermi, the physicist, walking out of the cafeteria one day said, "Where is everybody?" And, you know, I think I've got this backwards. I'll explain the paradox in other words. I think I've switched some slides in here. But here's, and the reason is it takes almost no time, cosmically speaking, to settle the Milky Way if you choose to do that. If you choose to send yourself off, something off at 1% of the speed of light, which is something we can do now. We can send little cameras at 1% of the speed of light if we wanted to. And it would take almost no time to get our trash around the Milky Way. So if there are other civilizations out there, where's the evidence? And here's one answer. I think I've solved the Fermi paradox. Scientists thought that our galaxy should be teeming with technologically advanced aliens. Physicist Enrico Fermi wondered, where were they? Why hadn't the aliens contacted us? Were they destroyed by their technology? Were they not technologically advanced enough? I believe that alien civilizations stagnate once their technology hits the smartphone phase. And here's 2 aliens. We should explore space, but first let me take some selfies. I gotta check my Facebook page. A marvelous thing. And here's the slide that should have started off, showing a rough position in the Milky Way. The radio waves we generate here get to the center of the Milky Way in under 30,000 years. At 1% the speed of light, we cover the Milky Way in 6 million years. 6 million years is long in the lifetime of you or I, but it is not long in the span of life on Earth, or potentially a communicating civilization. And the point I want to make is that space is big. It's really, really big, but time is bigger. And here's a fun thing that you can just amuse yourself with someday. Let's say we decided to take a walk here in Greenbank, all of us. We could all walk a mile. And we have a day to walk a mile, you know, down to the GBT and back. It's more than a mile. So let's say we walk a mile, then we rest a day. Then the next day we walk another mile, then we rest a day. Then we walk a mile and rest 3 days. In 1 week, we've gone 3 miles. At that rate, it doesn't take many years and you're on the other side of the Mississippi. And by the time the kids who were born when we set out get their driver's license, we're in Los Angeles, where they will certainly need a driver's license. And so the United States is really big, but time is bigger. There's time for things to go on. And in terms of the history of the Earth, this was a diagram shown at a meeting we had here on oxygen and planetary atmospheres. Here's the start of the Earth as a stable structure. And over on the right is today, modern day. So we have this blue curve is the amount of oxygen in the atmosphere. For a while, we didn't have oxygen, and all of a sudden we had oxygen. And then you have first animals appearing over there. First life appears all the way back here. First complex life appears over here somewhere. But on this scale, that is 6 million years. That little line is with the 6 million years. So it's really nothing on the scale. And what this means is, if we had a sister planet somewhere else that started off with us exactly the same time, went through exactly the same phases, but was 1/10 of 1% more efficient, by now they'd be 6 million years ahead. That's all it would take. So thinking about SETI, it may not be a question of who's out there to communicate with, but synchronizing development. 6 million years ahead, it's hard to imagine what it's going to be like here 600 years ahead. So, lifetime of a communicating civilization. We don't know. But it is interesting that when Jansky announced his discovery of radio waves from the universe, we made the front page of the New York Times. And the last item here, no evidence of interstellar signaling. So this was on people's mind back in 1932. Could somebody be picking up radio waves? Jansky, we don't think of as an amateur astronomer. He was, what happened here? We don't think of him as an amateur astronomer. We think of him as an engineer, which he was, who accidentally did some astronomy. Which brings me to this topic that I've been curious about for a while. What's more important, serendipity or sweat? Serendipity is the lucky finding of something that was unexpected, but of a good nature. We know what sweat is, okay? What's more important in astronomical discovery, serendipity or sweat? And I'm looking at an audience that I'm sure knows about sweating to do astronomy. But let's go back. I'm not usually reading the Princeton Weekly, but I did a search a few years ago for the word serendipity and found in this issue of Princeton Weekly, Princeton astronomer recalls a once-in-a-lifetime star sighting. Alicia Soderberg, a postdoc, saw a supernova go off in the X-ray while she was observing it with a satellite. And it was a really remarkable discovery. And she described the experience as being in the right place at the right time with the right telescope. She says she won the lottery, okay? But those of us who know Alicia know there's more to it than that. And this was her advisor. He says, if you're active and energetic, it helps a lot because you manufacture your own luck in a way. And I think that's true. It's maybe not so easy to separate serendipity from sweat. In the same issue, this guy set a record for push-ups in 20 minutes and 50 seconds. Same issue of the Princeton thing. Now that's sweat. Okay, there's no question that is sweat. And so here's Jansky, He was sort of an amateur astronomer. He's sort of the first amateur radio astronomer, although he was paid to do the work. And he noticed the extra signal that moved with the stars. Okay, Grote-Reber. Boy, talk about the definition of an amateur radio astronomer. Has anyone here been able to meet Grote? Is anyone around here? Toward the end of his life, he was spending summers here.
Yeah, I met him.
Okay, yeah, Tom, yeah. Quite an amazing guy.
Yeah, he always wanted, offered, you want a picture of me and you together? Okay, so I've got a picture of me standing next to him.
Yeah, he was a really interesting guy. This was shown as a young guy, proud as can be at the focal point of his telescope that, of course, we have out here. This was not serendipity. He was out to find the radio mission. He was out to follow up Jansky's work, and he did marvelously. This is an astronomer who's not so well known in the North, Ruby Payne Scott. She was a graduate of the University of Sydney and with her degree in physics was thought to be the most brilliant mathematical physicist in Australia at the time. During World War II, she and colleagues at the CSIRO worked on radar. And we're seeing one of the radar installations here. There's a ship entering, and the gap in the back is the entrance to the bay that Sydney is built around. After the war, her entire group transitioned to radio astronomy, and they started doing solar observations and discovered these highly polarized signals from the sun. You know, a lot of sweat, right? It's Australia. A lot of sweat. The sun didn't have to produce these things. It's hard to know. Okay, serendipity or sweat in this case. Let me just point out an interesting thing about our first three pioneers. Ruby Payne Scott was the first woman to do radio astronomy, period, and certainly one of the first radio astronomers in the Southern Hemisphere. Jansky, we know, died young, in his early 40s. He almost certainly would have been awarded the Nobel Prize for his discovery had he lived. Reber, on the other hand, lived to be the cranky old man that you remember. Just an amazing guy. Oh, is Sue Ann in here? Sue Ann spent a lot of time with Groot and can tell you some wonderful things. In fact, she wrote a piece in that book, but it was fun, about adventures with Groot. So he lived to see radio astronomy really become the international thing that it is now, and hated that. You know, he was a solitary guy. He just wanted to do things in his own lab and didn't really think much of. He said, if you're working at, say, L-band, 21 centimeters, your receiver is hotter than the sky. So basically what you're measuring is an impedance mismatch. You're not actually receiving signals. Okay, now that's both brilliant and nuts, but that was why he drove himself to work as low as possible, tens of megahertz, where for certain he knew which way the energy was flowing. Ruby Payne Scott had a different fate from these two, and I'm very curious. She had done something around the time of her service in World War II that was so unacceptable that when it was discovered, she lost her job and lost her pension too at the same time. She went from being fully employed to someone that could only get temporary employment. Does anyone here know what she did?
Got married.
Got married, yes. At that time, as a civil servant in Australia, a female who gets married is assumed to have resigned her position and forfeited. And her colleagues hid, they knew she was married, and they hid the fact because she was so brilliant to work with. But at that time, some administrator found out, and that was the end. She could only take temporary positions after that. And when she became pregnant with their first child, there was no way for her to continue a career, so she left astronomy. The New York Times a few years ago came to the realization that its obituaries were dominated by white guys. And they thought, well, maybe we can do a little retrospective catching up and be more just. And so there was a obit for Ruby Payne Scott that finally appeared in 2018, many, many decades after her death. You notice I didn't have a title for this, and please suggest titles later on, all right? This is my sort of ramble through radio astronomy, but what I want to do now, while I'm still talking about serendipity and sweat, is jump to the North Atlantic to Jan Oort, brilliant astronomer, discovered the rotation of the Milky Way, the Oort cloud, many things like this. And in the 1940s, the Netherlands was occupied by the Nazis, German army, and they started having belief tests for the various professors, not just if you're Jewish, but other ways to restrict their activities. And so the Leiden faculty resigned and went into hiding. But he still tried to do astronomy. And in fact, at an incident, which I don't have time to describe here, he was bicycling through the countryside and ended up meeting Hank van der Hulst, who was a young man also in hiding, because if van der Hulst had been discovered, he would have been sent to some labor camp in Russia by the Nazis. So the two of them got chatting. Oort said, if you're interested in physics, why don't you find a spectral line that emits in the radio so I can do Doppler shift and measure the rotation of the Milky Way. And this is a recreation of his presentation at what was an underground colloquium, a little meeting that was held to discuss astronomy during occupied and at the time of the occupation. And so I often think, you know, they said they recreated it after the war. Didn't anybody take a picture at the time? And I said, oh yeah, that's exactly what you want, is a picture of all these people getting together for this illegal activity at the time. And so every time I get grumpy about having to get out of bed in the morning to do some work, I think about this, think about what they went through just to do their own astronomy during the occupation. Well, the Germans left a lot of equipment behind. I don't know if I have, yeah. And this is, well, the 21 centimeter line was finally discovered by Doc Ewan at Harvard. We have his horn out here. He came here for the 50th anniversary and talked about that. It was expected to be a null result. They didn't know whether it would be an emission or absorption. And so Purcell, his advisor, said, you got to have a really good measurement for a null result if you want a thesis. It has to be, you know, much more accurate than a detection. And he said he came back from lunch one day in the winter. This was sticking out of the second story of the physics building. He came back one day in the winter to find the junior physics faculty were throwing snowballs and trying to get it into his horn. His comment was, the faculty can smell a failed experiment from a mile away, but it didn't fail. And they got in touch with colleagues, with Oort and with colleagues in Australia. And there were 3 papers published simultaneously in Nature about the discovery of the 21 centimeter line. And in fact, Oort had even made some astronomy out of that discovery. And then there were these radar dishes left over after World War II. Within a few years of the discovery of the 21 centimeter line, we had a new location for the center of the Milky Way. We knew about its rotation. Amazing set of discoveries, pure sweat. Fast radio bursts. It was alluded to this course that I'll talk about that again in a minute. But at the as I was doing this course for the great courses, I thought, what should the last lecture be? Well, it should be about the future. Okay, let's make prognosis. And one of the things I'm personally proudest about was, at that time I said, which was close to 10 years ago now, I said, fast radio bursts. Watch out for fast radio bursts. This could be really important. At that time, there was just one. Dunk Lorimer found this fast radio burst. I see you've had a talk about it because they're really amazing things. And for years, after this was discovered, they went back with Parkes telescope and spent hundreds of hours staring at the same spot in the sky, got nothing. The director of NRAO was very skeptical about the reality of these things for many, many years. But it was real, and it was found. And we now know that there are probably 1,000 of these things impinging on Earth every day. Only while you're looking here, they're coming from that spot. And I hope the person who talked about the fast radio burst talked a little bit about the intensity and what it would take to detect them. Oh, that's right, that's where I'm going. Because when I was a graduate student at University of Massachusetts, I was rounded up one summer along with all the others, graduates and undergraduates, taught how to do hard labor in the Massachusetts countryside to build this array. It's a terrible photograph, but that's the only one I could find. It is mini Arecibo's, 120 feet across, chicken wire mesh, a ring of telephone poles supporting a truss of simple steel, and then cables strung, pulled into a shape of a sphere, and then lined with mesh. And this was something that Joe Taylor and Dick Huguenin built in the early 1970s, mid 1970s, to do studies of pulsars. That is the kind of thing that could have detected fast radio bursts. In fact, here's a photograph then, it's much better, of planting the telephone poles. You can see when it wasn't a hard hat in sight, right? We were just out there in the fields. And not only that, this came from the UMass archives, quite amazingly. That's me. That's me. And if you see what I'm doing, and you see what the other people are doing, you realize it's black fly season in Western Massachusetts. But we were planting these telephone poles and stringing this cable. And there's Dick Huguenin over there on the left. Around the same time, he came to Green Bank with an array of small antennas. I'm really going to try to find out something about it, because by that time I wasn't at UMass anymore. I was working on my thesis out of Charlottesville. But he came here and set up an array of small telescopes, small antennas down on the site, because there was a theory that at the moment of a supernova explosion, there would be a pulse of radio emission. And he was out to find those. He never followed up for reasons I don't understand. He never completed that, but he could have found fast radio bursts decades before they were actually found, had he continued with that. On the topic of serendipity, this is Mort Roberts. He was my mentor when I was an undergraduate. He discovered the extended hydrogen rotation curve of galaxies and basically dark matter. And he said, the period dating from the first IAU symposium on hydrogen and galaxies, maybe that was probably the first IAU symposium, has been exciting and productive. The continued development of new instrumentation for both space and ground-based observations promises an even more fruitful period ahead. But it's more than instrumentation is needed, and this was typical of Mort. He would now quote Democritus. Democritus, over 2 millennia ago, described another vital ingredient: who seeks will find the good only with labor and pains. The bad, however, is found by everybody without seeking. A little bit of brilliance. I am converging somewhere, and it's going to go through radio astronomy, observing the invisible universe. This is the course I did that was alluded to. That's me. Look at all that hair. Standing in the set they built, especially for it. They even stocked it with old equipment from here and made up books and so on. And this is the crew it took to make it. The cameraman, one of the chief cameramen on the right, next to the set designer. The woman to my left was my science editor. She read everything and made suggestions. The producer, the woman in white there was fantastic. She's their reference librarian, and if I wanted a reference for something, she could dig it up and get permission or not to include it in the course. I had to write everything. They do scripts, and so you're standing there. There are 3 cameras. You've got to stand on this little hatch and read your own words on the monitor. But the director has inserted other things like this. Camera 2. Welcome back to our course on radio astronomy. The lecture is about, I think camera 2 was right. That camera 2 was one that moved around, so you had to kind of follow it. Camera 1, then you have to finish saying this and then read, oh, now I've got to move to camera 1, which is that one, I think. We move to camera 1, etc. And that's the exercise that you go through. You'll never realize how much spit you make until you have to talk continually for a half an hour like this. It was really quite the experience. And then it goes out. Anybody with a buck can buy it, and anybody with a buck and a keyboard can comment on it. And so I now know why actors are insane. You do this thing, you do the best you can, it goes out, and as I say, anybody can. William Faulkner, the Nobel Prize winning author, used to work as the postmaster in Oxford, Mississippi, and he hated the job because he said he hated being bossed around with any SOB that had 3 cents to buy a stamp. Okay, this is one of the first reviews. Professor Lockman's a very easy guy to like. That helps, given that it's quite a bit of it so basic, it's almost impossible to pay attention. Very unfortunate lost opportunity to explain this wonderful subject with at least a little depth. Okay, and then another one. I watched the first several lectures and presented with a lot of new information. My biggest criticism has to do with the subscripts for the hearing impaired. I assume they make it clear that this course is completely scripted and makes Dr. Lockman seem more boring than So as I say, I understand why actors are crazy. Look, let me wind down a little bit about astronomy and society, because I started off with talking about this amazing fusion of art and music in this electronics factory that was responsible for so much of the equipment that we use. As scientists, we have kind of a basic ethics that is truth, respect, and acknowledgement. And truth for us scientists is really easy compared to almost any other field. It's reproducible. If it's reproducible, it's true. If it's not reproducible, well, you wait till it's reproducible, but until then, it's not true. And so we have a requirement upon us to speak the truth and make it reproducible. And that's why we come down so hard on our colleagues who fake data. You know, in science, one strike and you are out, because we really depend on the honesty of our colleagues. And I keep telling students, this is not universal, as you will discover when you buy your first house, okay? You can expect your colleagues to tell you the truth, but the world is not like that. Respect. It really doesn't matter who you are that made the discovery. As an undergraduate, I was very lucky to make a fairly major discovery, and I took it to my advisor, Mort Roberts, who was involved in it, but he didn't realize what he had found. And yet I showed him the data and said, oh, we have to follow up on that. It's a respect for the product, kind of independent of the producer, and acknowledgement. You know, we acknowledge that we depend on so many other people that have gone before and give them credit. That credit is the important thing. This is a little thing I make sure I talk to visiting students about. Scientists and society. Galileo, of course, he said, what would we say of the learned here who have steadfastly refused to cast a glance through the telescope? Should we laugh or should we cry? Okay, still it moves, right? If you can't refute the science, attack the scientist. Pattern throughout history. Rachel Carson discovered that all those insecticides were not necessarily good for the world. And she was attacked as a communist sympathizer and a spinster with an affinity for cats. I swear, I prepared this slide 10 years ago. It has nothing to do with anything. This is an interesting guy, Ernest Winder. He discovered that cigarettes might not be healthy as they were being advertised at the time. And the tobacco industry put pressure on him not to publish anything that caused the disease, and the director tried to suppress his studies. The director of what? Memorial Sloan Kettering Cancer Center. Wow. Okay, and then here's the guy, Roland, who discovered that the fluorocarbons were not good for the atmosphere. Okay, DuPont chairman called the science fiction tale load of rubbish nonsense. That's cool. It was attacking the science, sure. It reproduced or it didn't. But then old aerosol age, called an age of the KGB, which is the attack on his person. And of course, we know the climate scientists and their problems. This is my last slide. And as I say, I hope that you could come up with a title for what this talk has been. It's a romp through radio astronomy from my point of view, with the acknowledgement that had I tried to get into anything more technical, you would have shown me how little I know compared to how much you all know. Ain't astronomy grand. Thank you.
You have a few minutes.
Oh, yeah, sure. If you're curious, I took this out my backyard. Was watching the rainbow move across the GPT. Oh, yeah, I have time for questions, certainly. Yes.
Just out of curiosity, the picture you showed of the timeline of discovery of exoplanets.
Right.
There seemed to be a cluster forming that was like sinusoidal.
Gosh, you know.
Why did that stand out to me?
You know, you're Angela Damery, who runs the Science Center, pointed that out as well. Let me go back to that, because there's a lot of information in that image. Here we go. Okay.
If you look at your dark purple clusters,
you're right. And that almost certainly has to be, I guess that's constant declination, and it is a planet-finding telescope that is more or less fixed. And so as the sky rotates, it measures the brightness of stars. Okay. That is my guess. This cluster down there to the left is the Kepler telescope, which just looked at one patch of sky and found all these planets. But yes, that's what that has to be. I ought to track that down. You're right, it's so obvious when you look at it now, especially in southern hemisphere. And so that, it looks like it crosses the plane at maybe -10 degrees. So that would be a southern telescope if it was pointed straight up. Yeah.
From the purpose of your presentation, it looks like the biggest limit to our willingness and possibility to discover is the speed of light. You know, if we could have a problem, fix it, we would be a lot easily reaching places where things could happen and we could find out. The question I have is there any professional, serious study that challenge the limit of the speed of light today?
Yes is the answer. I'm confident that there is, because if you're starting out as a young physicist, you don't make your name by confirming something that everybody else has found. You make your name by showing that everybody else was wrong. And there are, I was hearing something recently. Yeah, we had a wonderful little lunch discussion with our summer students and other people on the nature of time, which is really interesting. Because, well, we know what a thermometer does, okay? It's sticking out, it comes into equilibrium with its surroundings and it measures temperature and everything. What exactly is a clock measuring? And we sort of tend to think of a flow of what, you know, can you prove that a second yesterday was the same length as a second today? Can you bring it around to compare them the way you can compare two weights? No, the people are digging into this because there are still some big mysteries at the fundamental level. And time is certainly one of those. I think Richard Feynman just gave up on trying to define time.
But we can measure it real accurately.
Well, we can measure it.
We don't know what we're measuring, but we can measure it.
Right,
accurately.
exactly. Yeah, we don't know what we're measuring, but we can measure it. But now the atomic clocks are so accurate and they depend, the rate depends on the local gravitational field. It's a general relativistic effect. But the center of the Earth is a complex thing that's moving. And so at the accuracy of our clocks now, no two run the same rate. Okay, because they're in different gravitational environments. So, yeah, did you?
Is there any sort of collaboration between, you know, the SETI group and the respectable UAP community as far as interaction between the two, or?
You know, I'm sure that there is, although I don't know of it. SETI is funded through the Breakthrough privately, and all their data, by the way, is available online. My take on the UAP thing is, and if I had a laser here, I would demonstrate it, but if I take a laser and go zing, zing, over 1 second, period, that little speed is going like 10 miles an hour. If I were shining that spot on a low-flying cloud, it would be, you'd see a thing going 1,000 miles an hour that stopped and turned around and went 1,000 miles an hour back. So that's my guess as to what the UAPs are. But this was an interesting thing because back when I started thinking about this talk, I thought I would have a slide that dealt exactly with that, with the idea that you have all these FM transmitters around, and so they're just dumping their power into space. An object like a plane is going to reflect those. So if you have a way of looking for reflected FM, then you have a way of probing things in the atmosphere. I don't know what kind of sensitivity it would take. You'd need more than one to make sure you weren't seeing some multipath sort of thing.
We see planes all the time.
Yeah.
We're looking for meteors.
Oh, really? Okay. Yeah.
Passive radar.
Yeah.
And it's quite distinctive because they travel the Doppler associated with where the plane is and you.
Mm-hmm. So it's happening.
So you can, the eyeball instantly makes a calculation. Oh, that's not a meteor.
Uh-huh. It's an airplane. Yeah. Very cool. Let's see. And then, yeah.
You were talking about serendipity versus sweat. I'm just curious as to the Lockman hole, was that a serendipitous discovery, or were you specifically looking for holes?
I was looking. I heard this. I'm actually writing a little essay on this because enough people have asked me about it. I was in an auditorium, I don't think it was this one, and somebody came up, one of Ort's students showed up and said, there's neutral hydrogen in every direction of the sky. And I thought, he can't know that because of scattering off, because of side lobes, scattering off feet support legs. He can't know that. And I thought, what if there was a hole? How could you find it? And that was then, just for the heck of it. As it turns out, I was collaborating with some people in the X-ray who said, you know, if you found a hole, that would be really good because it doesn't take much gas to absorb X-rays. And so if you found something, then the X-ray satellites would be looking at that to look deep into the universe. And it took a while to figure out how to compensate for scattered radiation. That guy, Dick Huguenin, taught a radio astronomy class that I was in. And I've made in my notebook, never work on galactic hydrogen, the side lobes will kill you. And so it was several things that came together, but, and I looked and didn't find, well, I didn't find a hole, but I found a really low spot that I had nothing to, if it was up to me, it would have a different name, okay? But it is the site of a lot of work. And in fact, the reason why the Green Bank telescope has an unblocked aperture in part derives from my interest in making side lobe free measurements.
So sweat, definitely. Could you say what you said about atomic clock again?
Yeah. There's a general relativistic effect that makes clocks run differently depending on the gravitational field that they're in. And with enough accuracy, you can look at it using a clock to measure what's below you, what is producing the gravitational field on Earth. And we are at or close to the accuracy so that a clock over here feels a different field than a clock here. So they run at different rates. There's, if you get interested in time, you don't have to go very far on the internet to see some really amazing, mind-bending articles. And I'd be happy to give you some references on that if you're interested.
We have a listserv called the Time Nuts, including the guy who ran up and down Pikes Peak with the back full of cesiums.
Yeah. I recommend a paper by Harvey Brown, who I only know about this paper because he turns out he's a long lost second cousin of my wife's, who was a professor of the philosophy of physics at Oxford. And he wrote the paper that starts out with asking us to think about the difference between a thermometer and a clock. It's really
Well, not being a physicist or an astronomist or anything like that, I'm always curious how that kind of concept is taken into perspective when you're studying the light source from so far away, but yet we keep the speed of light constant.
right.
And so to me, that's just one of those, as a systems engineer, you always worry about your assumptions. And so that one always just stands out. So
Yeah.
not because I'm educated in it, it's just one of these things.
That seems ruggedly consistent. The consistency of the speed of light over the 100 years it's been discussed. You know, when I started my career, there were big questions as to whether the laws of physics were the same in different parts of the Milky Way or even the different parts of the universe. And the answer has always been yes, and it's a whole lot simpler than it could be. I was on a paper once that got a bunch of, the whole thing about the Lockman hole is really knowing your instrument. It's an instrumental effect. And this one paper that preceded it was about the galactic center. They had found hydrogen emission in a recombination line, but no helium. And at that time, helium was really thought to be the linchpin to understanding the evolution of the universe. You make hydrogen and helium early on and not much else. So wherever you have hydrogen, you should have helium. And the center of the Milky Way is kind of a special place. We didn't know it at the time, but there's a black hole there. And so the inability of the community to find a helium recombination line was an interesting thing. So Bob Brown and I went out on the 140-foot and we determined that it had been an instrumental effect of very low level standing waves. We removed that, found a normal helium abundance, and that ended that entire discussion. Yes.
What do you think an organization like SARA, which we're pretty much international now, what's the best thing we could do to improve radio astronomy for professionals and amateurs and education, all that?
You know, I've thought about this a little bit, but and this is why I wished I'd heard some of the talks previously. What's really interesting in the last while is time domain astronomy. So we know that the universe is changing now, and fast radio bursts are just the tip of the iceberg, probably. The problem with an amateur or professional working on time domain astronomy is that there's lots of other things that vary with time. And so you need simultaneous measurements from separate sites. That's what you want. And even, well, fast radio bursts, you know, fast radio bursts are so distinctive that it's probably not going to be confused with something else. If you have a high time resolution and enough bandwidth to see the dispersion, then that's pretty distinctive. But the Rubin telescope, and I must say I was very lucky to do a postdoc with Vera Rubin. The Rubin telescope is going to start scanning the sky every couple of nights and turning up thousands of variable objects in the optical, some of which almost certainly will be variable in the radio. Again, I don't know the sensitivities that would be required. I gather there was a talk about giant pulses from the crab, which is obviously something that you could do and is unlikely to be mistaken for anything else. That's the kind of thing I would think. See, I'm thinking purely from the scientific point of view. We can't look at professionals. By the way, I retired in January. I'm emeritus now. So I am now an amateur radio astronomer. I will be before the end of the day.
Another comment there. Back in about 1992, Jeff Lichtman in the SARA organization, one of the starters, and Chuck Forrester, who's unfortunately now deceased, were out pursuing high energy pulses, which would be essentially the same thing as fast radio bursts. And they'd even gotten a high school student with a radio telescope on the same frequency, some distance away, and they never got a correlated burst between different receiving sites, but they were looking at it, they were seeing these bursts that probably most of them just EMI of some sort.
Yeah.
But yeah, if something happens that's real, sorting it from EMI, a couple of observers separated by enough that they wouldn't get the same EMI about it. But anyway, they were thinking about it seriously then, and it's just now we're actually showing up with, it actually happens.
Yeah. And you know, there's lots about the atmosphere that we don't understand. You're probably familiar with this spurious result of Clarions, or what was it called, with the Parkes radio telescope, where they found which ones? Paratons, right. They found what looked for all the world like a fast radio burst. Only the problem was it was showing up, they have an array receiver, so they could tell that it had to be coming from on Earth somewhere. It was not celestial. And they thought it might be some phenomena due to thunderclouds and so on. And it was finally discovered that what it was the microwave oven in the visitor center. If you were in a hurry and you opened the door before its cycle was complete, what you had was a burst of radio waves from a cavity whose size varied as the door opened, which would give you a chirp. And I have seen that microwave oven. I've been to Parkes, and they have a visitor center right there. You can be observing at Parkes on like a Sunday morning, and it's dead still in the lab and on the telescope. You open the gate and a little fence, and you go through, and there's a party going on in the visitor center. But I looked at the microwave, and I thought, geez, we would not allow an unshielded microwave. That's what it was. But that, you know, you read recently about gamma rays from thunderstorms. There's a whole lot of stuff going on in our own atmosphere that we just don't understand. Some of that may be producing radio emission. I don't know. Should I wind it up now? I'm happy to stay around and take more.
Do you plan to have any other course with the teaching company?
I have pitched to them a year ago a course on SETI. And because it seems to me that that's really interesting. And I could talk about technical aspects. I could talk about cultural aspects, which obviously interest me as well. All this sort of stuff. But they said they didn't think that there was interest. Now, my guess is that means they have somebody else doing it. Okay. But that's all I know about.
Do any of the online participants have questions? You must have answered every question.
How about my question? What's the title of the talk?
The title of the talk is the last slide, Ain't Astronomy Grand?
Thank you. Thank you. Listen, I'm happy to, this seems like a good time for me to take a break.
Okay.
I'm happy to be, stay around and chat or whatever.
Wonderful. Okay, we will just take a break and let you mingle. Thank you so much. Here's a little something. Hope you'll think of us kindly once in a while.
Well, I fully intend to be a member now.
Okay. And an official certificate.
Ah, thank you.
Yeah. Thank you, sir. Certainly do appreciate it.
Thank you, all of you, for coming to Green Bay. So much of